Here's the periodic table. And as you see, it can be broken up into different sections. So there's the S, the D, the P, and what it's telling you is that at the end of the electron configuration, the S block ends in S's, the D block ends in D's, and the P block ends in P's, and the F block ends in F's. So it's S, D, and P, and F. And below that, if you look here, it's giving you the very last part of the electron configuration. So just so if you're doing your electron configuration, you're trying to figure out what it is, there it is. Also, if you follow along, let's say you get to sodium, and sodium is in the first column and it's the third one down, so it's 3s1. If you start out at the top where it says 1s1 and make your way all the way down to 3s1, that's the electron configuration for sodium. Also, some things to notice about this are the period numbers, which periods are horizontal. The period numbers are the same as the highest n level. So the first period is 1s, and the second one is 2s and 2p, and the third one is 3s and 3p, and the fourth one, the highest n level, is 4, and then the d's always go down by 1. So it goes 4s1, 4s2, 3d. So if you follow this periodic table trend, you don't even have to draw the Aufbau principle out at all. So if I was going to do sodium that ends at 3s1, and following along at the top, it goes 1s1, 1s2, 2s1, 2s2, 2p1 all the way to 2p6. So far I've got 1s2, 2s2, 2p6 is full, and then 3s1. And that's my electron configuration for that. And then I've been telling you guys that there are 2 different numbering systems, and this periodic table here shows you the AB numbering system, which is more useful. It basically, you don't have to worry about the B numbering system too much because it's not terribly useful right now. But if you look at the A numbering system, it's 1A, 2A, 3, all the way to 8A. And you get some trends along with that, like all of the valence electrons have the same number of valence, well, all of the groups, those are up and down columns, have the same number of valence electrons as they do their group number when you're using the AB system. So group 1A is 1 valence, group 2A is 2 valence, 3A is 3 valence, and so forth, all the way to 8A, and that's 8 valence electrons, and you get an octet, and octets are extremely stable. And then here is just another one, but in this one, they give you a little bit more information. They're showing you the Ds, and this is nice where you can kind of take a look visually at the little things that change for the d orbital. If you have a half-filled d orbital, it's more stable than if you have a half-filled, a completely filled s orbital and an almost half-full d orbital. I'll show you that in a minute or two when we get to the d orbital stuff. Let's see. All right, so if you're looking at the atomic size, and this is from section 310, you'll notice 2 things. One is that as you go down a column, it increases in size. These are atomic sizes, the atomic radius. So you go down a column, they get larger. As you go from the left to the right, they get smaller. So the small ones are in the upper right-hand side, and the larger ones are in the lower left side. The largest atom is francium, which is the very bottom one in group 1, and the smallest one is fluorine. As you go down a column, they get more and more and more electrons. The n level increases. So like I was saying, the period number increases As the period number increases, so does the end level. So period 1, the end level is 1. Period 2, the end level is 2, and so forth. As you increase the end level, you're increasing the orbitals that get farther and farther and farther away from the nucleus. And so that's causing them to get larger and larger. As you go from the left to the right, they increase slightly in electrons, but not nearly as much as if you go down a column. They only increase by a few electrons, usually no more than maybe 18 electrons at the most. But that's not going to matter as much as the effective nuclear charge. And the effective nuclear charge is going to increase as you go from the left to the right. And the effective nuclear charge is what's holding the electrons in the atom so that they don't just fly away from the atom. It's the nuclear charge. So as the effective nuclear charge increases, it's got more of a pull, so it's pulling the electrons in closer and closer and closer, so that as you go from left to right, they get smaller and smaller. And, sorry, there are a couple of other things as well. I will show you that now. All right, so we have the periodic table, and it goes going this direction and going this direction. The radius, the atomic radius, or the size, increases. So it gets larger. So this is big, and this is bigger, right? And we have a couple other things. We have what's called ionization energy. And ionization energy is the energy required to pull off an electron, or to pull off a mole of electrons. And, to pull off a mole of electrons. So if the electrons are held really tightly, they're very hard to pull off. The ones that are held very tightly are over here. So the ionization energy has the opposite trend. You will have a periodic table. So this is the nucleus, the size of the nucleus. And this is the increase in ionization energy. So as the ionization energy increases, the atom gets smaller. And I think a good way to do this. All right, so let's say we have sodium. So it's 1s2, 2s2, 2p, 6, 3s1, right? So ionization energy has to do with pulling off electrons. So the 3s1 orbital electron is a valence electron. That one's easy to pull off. So it does require some energy, but not a whole lot of energy. So if we delete that, then we're left with the core electrons. Once you get to the core electrons, it's really hard to pull those off because they're extremely stable once you have a noble gas configuration, which is that's all that the core electrons are. So the ionization energy is huge. There's a really big jump. If you go to the textbook and you take a look at, let me show you, I'll actually show you the picture from the textbook so you don't have to imagine it in your mind. Makes it a little harder. All right, so looking at the textbook, all right, it's talking about ionization energy, gives you the definition up there. It's talking about with magnesium, magnesium generally has 2 valence electrons. So you pull off the first valence electron, it's about 738 kilojoules. You pull off the second electron, it's not that much more. By the time you get into the third electron, you start pulling off much larger numbers in that. And here's the chart that's showing that. So if you look, let's take a look at lithium. Lithium has one valence electron. To pull off one valence electron, or 1 mole of them, it's 520 kilojoules. But it has a really big jump when it goes to the next electron, and that's because it's gone into the core. So you see the little red step looking thing? That's the difference between the core electrons and the valence electrons. Valence electrons are shown on the left, and when you're pulling off the core electrons, that's shown in the right. So if you just look at boron. Boron has 3 valence electrons, and they're 801, then 2,426 for the second one, 3,660 for the next one, and then 24,682. It was from 3,000 to 24,000. So like 800, 2,000, 3,000, 24,000. And the reason of that giant jump there is because it's pulling off core electrons. And you can see the same thing pretty much all the way down. Even if you're looking at neon, and neon is a noble gas, so it's hard to pull off any of those electrons. But by the time it gets down past the first, all of the first 8 electrons, when you get into even to the core electrons of neon, it goes from 23,000 to 115,000. So if you're looking at this chart and you don't have that little step thing there, you can tell where the core electrons start just by looking at the numbers, because as soon as they make a big jump, they've gone into the core electrons. And so that's the main thing there. No. You don't need to know the exact numbers of the ionization energy. Not at all. You just need to know the trend, that if you were given something like this, you could tell where the core electrons were being pulled off, because there would be a large jump. So you definitely don't have to memorize that chart. That would be a nightmare. Yes. Yep. Okay. Let's go back to the notes. Or let me see what I want to, if there's anything else. Sure.
Do you know, how many problems will be on the test?
Probably between 20 and 30.
I see. Thank you.
You're welcome. Is that a good number? Do you want more? You want less? That's good. Less? Nope. Okay. You'll be given the full class period, so 50 minutes. Kind of like the reading quizzes, but also with some math problems thrown in there. All right. So I want to go back to the textbook. And I'm going to go back one section to section 310. This is where it was showing the trends in atomic size. So this is what we were going over on Friday. So if you look at this picture here, it's showing that lithium is kind of, largish compared to if you go all the way across to fluorine, which is F. And that's because the effective nuclear charge increases as you get over toward fluorine. Because the core electrons stay the same, but the number of valence electrons slightly increases. But as you go down from lithium to sodium, you're adding, 30 electrons there. And as you go from sodium down to potassium, you add a whole bunch of electrons there. So every time you go down an n level, you're adding a bunch of shells of electrons to your atom, so it gets bigger and bigger and bigger. If you look down at the bottom, the largest one they're showing on this chart is cesium. Francium's actually larger. But you can kind of think of cesium as like a fluffy marshmallow. By the time you get to the outside electrons, or the valence electrons of cesium, it's easy to pull them off because they're really far away from the nucleus. So the ionization energy is not very high for cesium. Because the electrons are so far from the nucleus, they're loosely held, it's easier to pull them off. Now if you go to the upper right-hand corner and you look at fluorine, fluorine is really tiny. Those electrons are really, really close to the nucleus, and the nucleus has a good hold on them. And that's the reason it's so small. And if the nucleus has a really good hold on them, that makes it really hard to pull off the electrons. You can also see a couple of other trends. Fluorine is only 1 electron away from being neon. So it's more likely to gain an electron than to lose 7 to become like helium. On the other hand, if you look at lithium, lithium is 7 away from neon, but only 1 away from helium. It's got 1 more than helium. It's a lot more likely to lose 1 electron than to gain 7. That's why the metals tend to lose electrons and the nonmetals tend to gain electrons, because they're all trying to get to the nearest noble gas configuration. And then when you have ions, there's a trend in ion size too. If you look here, they're showing you in the first box on the left, where it's lithium there. The neutral lithium is large, and the positive lithium has had an electron pulled off. So needless to say, it's just the core electrons left. They're held very closely, and so it's a smaller atom, or it's a smaller particle, I guess. The ion is smaller than the neutral atom. However, if you look over to the right, you'll see oxygen. The neutral oxygen atom is smaller than the negatively charged oxygen atom. That's because electrons have been added, making it larger. So as you add electrons, you're adding rings around the nucleus, making it larger. As you pull off electrons, you're removing rings, making it smaller. Actually, that would be called electron affinity, and that's in Wednesday's lecture. It's called electron affinity, and that is actually what we're going to go over. And yes, there is a way to calculate that. Sure. All right. So if you take a look, let's go back to the periodic table I have up here. If you look here, take a look at fluorine. It's in column 17 there. It's really small. It's 1 electron away from neon. To get to neon, it has to gain an electron. What they're showing there is not like atomic number, those numbers there. Those are atomic radii, so you can kind of ignore those for now. So fluorine has to gain 1 electron to be like neon. Neon is extremely stable. So it's a lot more likely for fluorine to gain an electron. On the other hand, if you look at lithium, lithium is 1 more electron than helium. Helium is noble gas, so it's very stable. So if it lost an electron, it'd be just like helium. And then we talked about the ionic size. Let's see. You're welcome. You can gain extra points on it, and that will be by showing the ACS book that you bought. I'm just going to get you to submit a copy of the front cover with a piece of paper with your name on it across the front cover, and then that's it. If you have a PDF, then I guess just take a screenshot You can send me a screenshot. So that would be fine. All right. So let's go back. There's one more thing I wanted to show you. Okay. Well, it was before this, I think. Let's see if it was one back. Sorry, guys, this might be making me dizzy. All this extra scrolling. All right. It's not there. All right, so let's take a look at transition metals, transition metal ions. All right, so with the transition metal ions, transition metals have they're all found in the D section of the periodic table. So, for example, if you look at nickel's electron configuration is argon 3d8 4s2. Nickel can make a 2+ ion. They're called transition metals because they have different ions that they make, not just a single one. For example, iron can be +2 or +3. So they can transition from one ion to another. That's why they're called transition metals. So with nickel, on the left of this equation here, you see the neutral nickel. And on the right is the positive ion. If you're trying to write the electron configuration for an ion, first you write out the electron configuration for the neutral atom, like they've done there on the left, argon 3d8 4s2.
Yes.
And then if you look at the charge, it's +2. So for the transition metals, they're always going to be positive. They're not going to be negative. So you're always going to have to remove electrons. But the question
I'm
sometimes
not
is,
sure where it's at, but there's like a student center here, and you can go in, and then there's people at the door or the store and stuff that they might know where it is. If you go in that market right there, that building, there's like other people who work at this school, and they would know where it is.
Ion.
No problem.
You have to remove electrons from the highest energy level first. For example, here, 4s2 may not be the highest level because the D's are slightly above it. But when you remove electrons, you have to remove it from the 4s first. As you remove them, the energies change slightly, and that's why you have to remove it from the 4s. So, for example, if I was going to do, or just looking at how they did the ion for nickel here, it's argon 3d8 4s2. We're trying to make a 2+ nickel, so they took off the 2 electrons in the 4s, and then that just made it 3d8. And then you see they wrote +2 electrons. That just means they've pulled the electrons off. Exactly. Highest number first instead of the SPDF. That is correct. All right, let's see what else. Okay, so if you look at this practice problem, it gives you a good example of a practice problem for ions. It'll ask you what the electron configuration is of a transition metal ion. And here it's asking for 2 of them. It's asking for 2+ and, okay, we're almost done. For 2+ and 3+. So with 2+, you're removing 2 electrons, and with 3+, you're just going to remove 3 of them. So if you look at the bottom, not the bottom, in the middle where it says analyze, That's the neutral iron. It says argon 3d6, 4s2. That's the neutral iron. So when you're making 2+ iron, you look and you say, what's higher, 3 or 4? 4 is higher, so then you start pulling electrons from the 4s. So since you have to pull 2 of them, both of them are gone. Now, the 3+, you have to remove 3 of them. If you're removing 3 of them, you do the same thing. Say, what's higher, 3 or 4? 4 is higher, so you pull off those 2, but then you have to remove a third. So that's when you go in to start removing the d orbitals. And it's okay to remove those because they're not exactly core electrons. Another thing to note about transition metals is if you're trying to figure out how many valence electrons a transition metal has, you can't do it by what column they're in. You have to write out the electron configuration. And if you're looking here at iron, it's argon 3d6, 4s2. And the valence electrons are in the highest n level. So 4 is the highest n level. There are 2 electrons in it. So it has 2 valence electrons. If it ended in like 4s2, 4p1, then you would add all of the ones that are in the n equals 4 level. And that would be how many valence electrons it had. The core electrons for this problem would be everything that aren't the valence electrons. So in this case, the core electrons would be argon and 3d6. Technically. Because they're not the valence electrons. You have the valence and the core. It's a lot easier to distinguish between the two when you have the main group elements because the valence electrons are everything after the noble gas. The test is up to 312. What we're going to do on Wednesday, 312 is like 4 minutes worth of explanation. It's just talking about the ionization energy. We're not going to have a quiz on Wednesday because I want to have more class time. And we're going to finish up section 312 quickly. And then I want to do some practice problems with you guys so that you get some practice before the test. So it's kind of going to be a review day. And hopefully that will help out a little bit. Or hopefully a lot, but you know. Okay, so the best way to study the practice exam is make sure you've done all your reading. Make sure you've done the best you can on your homework. If you're still not understanding it, at the end of each chapter are practice problems. So if you go down, for example, in chapter 3, looking on the left, you'll see the periodic table. If you click on summary, it's going to explain the concepts first, and then it's going to give you all of the formulas, and it tells you on the left the type of problem those formulas are used for. And then below that, it gives you practice problems. So the more you practice, the better you become with these. The answers, I believe, to the odd questions are in the textbook. So some of the practice problems I have worked somewhere in the notes, but I may spend some time once I get caught up on the emails working some practice problems, just so that if you're practicing, you can see what they're supposed to be worked like. Maybe I'll work like the odd ones or something, or at least some of them. Okay, good, good. Yeah, the tests will be multiple choice. And you will do well in the test, Jackson. Working the practice problems in the book are the best. I would say, yes, I would not just work the math problems, but work the concept problems as well. And it's not just for chapter 3, because if you look, chapter 2 has it as well. And then chapter 1 also. So chapter 2's got the summary here. And then it's got concepts and equations, which there's not a bunch of equations in that section, but it kind of explains stuff. And then it's got some problems for you to work. And then chapter 1 also has some practice.